Chapter 9, Section 5, How Vector Norms Shape AI Decisions. Imagine two users who love the exact same movies, but one gives stronger ratings than the other. Should an algorithm treat them as different? In this section, we will show how mathematics, specifically inner products and vector norms, helps us focus not on how much, but on what kind of preferences people have. You will see how this idea powers clustering, recommendation systems, and text search engines. Let's dive into the hidden logic behind measuring similarity in data science. In this section, we will explore the practical applications of the two key concepts, the inner product and a vector norm. We will see how they are used in data science, particularly in feature normalization. Let's review by understanding why we care about vector length and how we measure them. A vector norm is a number that tells us how long a vector is. You can think of a vector as a list of features. For example, a person's preferences across different movie genres. This vector represents that the user gives 3 for action, 4 for comedy. The length of this vector gives us a sense of how strong or intense the user's overall preferences are. Just like how a long arrow points far from the origin, a long vector shows strong preferences. We use the inner product to define the norm. For example, the length of vector 3, 4 can be computed in this way. So, the length of this vector is 5. The inner product of a vector with itself gives us the sum of the squares of its components, which, when square-rooted, gives the vector's norm. In data science, we often deal with high-dimensional feature vectors. For example, user preferences, text embeddings, or image pixel data. When we compare two such vectors to see how similar they are, we need to be careful not to let the length of the vectors affect our comparison. Let's consider a simple example. These vectors represent user A and user B's preferences. At first glance, these users seem very different. But wait. The second user's preferences are just twice as strong, not different in direction. So, to compare them fairly, we normalize each vector, scaling it so that its length becomes 1. This removes the effect of how much and let us focus on what kind. Normalization means transforming a vector so that its length becomes 1, while keeping its direction the same. Why is this useful? Let's revisit our two users. V equals 3, 4. Norm is 5. W equals 6, 8. Norm is 10. At first, they seem different. But when we normalize each vector, we can clearly see that they are pointing in exactly the same direction. The users may differ in intensity, but their pattern of preference is identical. This is critical in many machine learning applications. Let's go through concrete applications where normalization using vector norms makes a big difference. The first is clustering. When clustering users, documents, or products, we often use Euclidean distance to measure how close two vectors are. But without normalization, longer vectors, even if they share the same pattern with smaller vectors, With normalization, clustering is based on direction, not magnitude. So, the algorithm captures behavioral similarity, not just strength. The second is cosine similarity. It is often used in text analysis and recommendation systems. In natural language processing, word or sentence embeddings are normalized before comparing documents. That's how search engines or chatbots know that buying a ticket and purchasing a pass are similar. Cosine similarity is defined in this way. This measures the angle between two vectors, ignoring their length. But to make cosine similarity work well, vectors often need to be normalized first. Let's wrap up. The norm of a vector is a way to measure its length. It is computed from the inner product. Normalization scales vectors to unit length, helping us focus on direction, not magnitude. It is essential in real-world applications, clustering, similarity search, text analysis, and more. Thank you for watching. Please thumbs up and subscribe to my channel.